Well, you heard about it so much in the last video, so let's talk about simple harmonic motion, what it actually is. So simple harmonic motion has to do with periodic motion, which is just any type of motion that repeats itself in a fixed time period, okay? So that's what periodic motion, and so simple harmonic motion is just a type of periodic motion where the restoring force is directly proportional to the displacement. Okay, so we represent this by like a mass on a spring, but pendulums work this way, right? The restoring force is directly proportional to the displacement, i.e. you displace something more, then the restoring force, or the force that works to restore something, is going to be changed by the exact same amount. Okay? And so that's what simple harmonic motion is. It's the type of periodic motion. So it's a motion that's repeating itself, but depending on how much you displace something, it's the restoring force works just as hard as to undisplace it, basically. Okay, so pendulums and masses on springs are kind of the two major things that we go over when we're looking at simple harmonic motion. Okay. So a mass on a spring looks like this, where again, here, if you take this and you compress it, right? So push it upwards, then it goes up here. And then of course, it's going to come back to its equilibrium, but that restoring force is now trying to push it down because of course, it needs to be pushed down because it's counteracting the fact that it was pushed up. And so then it's going to go all the way down, and the displacement, this displacement should be the same as this displacement. Okay. But one's being compressed and one's being stretched. And it will then, if there's no friction, we'll just go back and forth and back and forth and back and forth, and we'll do this forever. And the graphs of all, simple harmonic oscillators will always look like this. They'll always have this wave motion. Okay, so that's always what the graph of a simple harmonic oscillator looks like. So if something makes a graph like that, where it's going up and down and up and down, because this is displacement over time, right? So if this was, right, if you were looking at a displacement time graph, this would be your displacement, this would be your time, of course, and that's what's happening to the displacement. It's going above and below, and above and below, and above and below. Okay, and so that's also what the graph of a displacement time graph. That's what the graph of a simple harmonic oscillator will look like. It'll just go up and down and up and down, and it'll just keep doing that forever. Okay, so that's simple harmonic motion and how it works. So we make a few assumptions when we're talking about springs as a simple harmonic oscillator. So what are some of those? We're going to assume that the mass of the spring itself, like this part, is 0. Okay, not the mass on the spring, but the mass of the spring itself, we're going to assume that it's 0, or at least it's so much smaller compared to the weight that that it's put on the spring, that it really just doesn't matter. Okay, we're also going to assume that, of course, the spring slides without friction, because if it doesn't, well, of course, you've probably seen this, where if we have a spring, it's going up and down and up and down and up and down. Eventually, it doesn't go as far up as it did before, it doesn't go down as far as it did before, and eventually it will come to rest, because that's just what things do when there's friction. So if we're talking about a true simple harmonic oscillator and a spring on a mass on a spring, then we're going to assume that there's no friction. Okay? So for a spring, what is equilibrium position? We have gone over this a little bit. That's the position in which the motion will come to rest, right? So if you just put a mass on a spring and just let it hang there, and where does it want to go to rest? That is equilibrium position. Okay, so let's talk about the restoring force a little bit. So this is an elastic force, wow. And that's basically, what is a spring always trying to do? It's trying to return to equilibrium. Okay, so that's what the restoring force does. It returns it to equilibrium, but then a lot of the time, since, if you pulled the spring down or pushed it up, then the restoring force will overshoot. Well, actually, it pulls it up to equilibrium, but then since it already has some momentum in that direction, we know inertia, right? Object in motion stays in motion in that constant velocity unless acted on by an unbalanced force. In this case would be the spring force or the restoring force. So at the top, right, when something is oscillating, so at the top when it's really scrunched up, the force is always trying to restore it back down to its equilibrium. And then when it's like really, really stretched out, again, what's the restoring force trying to do? It's trying to restore it back to its equilibrium. Okay, and that's the restoring force. It's always trying to restore the spring back to its equilibrium. And this is directly proportional to displacement. And we found that out about springs, right? Because we remember that we learned that force of a spring is equal to negative K times X. Nice and directly proportional. So the more you displace the string, the more the force of the spring is going to try to force it back to equilibrium. Okay, so those are nice and proportional variables. Okay, let's talk a little bit about some simple harmonic motion vocabulary that I need you to know before I keep going here. So displacement, I know you guys know what displacement is, but specifically when we're talking about simple harmonic oscillator or simple harmonic motion, the displacement is really the distance from the equilibrium position, okay? So that could be for a spring where we know when the spring is at equilibrium, or even like a pendulum. You think of equilibrium as when the pendulum isn't swinging, it's just at its lowest height. Okay, so that's the displacement when we're talking about simple harmonic motion. The amplitude is the maximum displacement. So it's how much you the maximum amount that you stretch the spring or squish the spring or take the pendulum up. So that maximum displacement is called the amplitude. And that's going to be a really important one that's going to show up a lot. A cycle is one complete back and forth motion. Okay, so of course for a spring, it would be like going, if one was stretched out, its motion going all the way up until it's squished, and then all the way back down until it's fully stretched out again. If we're talking about a pendulum, it's one full back and forth, right? So if you pull a pendulum to the right, you see it swing all the way to the left and come back to the right, and the point that it's at the right again is one cycle, okay? And then, of course, the period of a simple harmonic oscillator is the time to make one cycle. That's measured in seconds. And the frequency is the number of cycles per unit time. We measure that in hertz. Hertz is seconds to the power of 1, or it's just 1 divided by seconds, right? Because, of course, we know that period is equal to 1 over frequency, which means frequency is equal to 1 over period. And period is measured in seconds. So that's 1 over seconds. And then somebody came along and was like, well, we don't want 1 over seconds as a unit because that's kind of weird. So we're just going to name it after an old dead white dude, and his name was Hertz, but we just use HZ for that. And I always put a little Z with a little tick thing through it so it doesn't look like a 2, because my Zs can look like 2s sometimes. Wait, does that mean my Zs look like 2s, or do my 2s look like Zs? I don't know. I don't know how to say that. I don't know which way it goes, but there you go. That's the Z that I write with the little ticky thing through it. So we know it's a Z. Okay, so let's talk a little bit more about a period of a simple harmonic oscillator. And I'm going to say specifically the spring one. So we went over period of a pendulum, which is also a simple harmonic oscillator. But now let's go over a period of a simple harmonic oscillator in terms of a spring going up and down, or back and forth and back and forth and back and forth. Okay, so it actually depends, the period, how fast it goes back and forth, depends on the mass and not the amplitude, which I think is kind of interesting. Remember, amplitude is how far away from equilibrium. So if you pull it further, the period is the same. So it just means it's covering more distance, but over the same time. Okay, interesting how that works. So here is an equation for a period of a simple harmonic oscillator when we're talking about one in terms of a spring. How do we know that this one is for a spring? Because what does K represent again? That's a spring constant. So if you're wondering, how do I remember which equation goes with which? Well, if it has k in it, that's a spring constant. So that should definitely be for springs, not for pendulums, right? So that's kind of the dead giveaway. This is also on your data sheet under waves. Okay, so I would take a look at that. So you'll have two equations for capital T, which is of course period. One is for a pendulum, and now here we have one for a spring that is oscillating back and forth and back and forth and back and forth. So let's just use this equation really quick just so you can get some practice with it. So we have the period of a simple harmonic oscillator. We call that an SHO for short. You've seen probably a few times SHM here, that simple harmonic motion, just because that's a lot of words to write, and sometimes we just don't want to write all those words because we're physicists, and the less words you have to write, the better. All right, so the period is 0.44 seconds. We want to determine the spring constant if a mass of 300 grams is attached. Okay, so remember, we got the period. Let's get my pen. There we go. Period is equal to 2 pi times the square root of m mass over k. Okay, well that's not too bad, but now we need to determine the spring constant, not the period. So I need to rearrange this for k. So we actually did this at the beginning of just like this entire course when we were going over rearranging stuff, and this is by far one of the most difficult ones. So remember, my first tip was to make sure you divide both sides by 2 pi first, and then I get t divided by 2 pi is equal to the square root of m over k. And let's go one step further. We didn't need to square both sides to get rid of the square root, so I'm actually going to do that right now. So I need to square this side, I'd square it and the square root would go away. So let's say that we already did that. Okay. So I'd square this side would end up being squared, because squaring the right side means that we get m over k. And then a lot of people had a hard time solving for k once we were here. So remember, I gave you a little trick, and that is the fact that t over 2 pi squared equals m over k is the same as this. I'm also going to flip them around. And so these are two equivalent things to say. So as long as I flip both fractions, that's weird that I did it that way, but I did, then it's still the same thing. Okay, so I flip both fractions, and that just gives me k on the top of a fraction, which makes life a lot easier. Okay, so what I end up getting, remember this squared has to go to the 2 and the pi, so that's 4 pi squared. I'd have to multiply both sides by m, so I'll have m up there, and I divide that by t squared. Okay, so that is how I solve for k. Let's plug in those numbers. 4 pi squared mass. Remember, we want kilograms, not grams, so that is 0.300 kilograms. Divided by period squared is 0.44 seconds squared. And what do I get for k? When I do that, I get 61 newtons per meter. Okay, so that is, I just want to do one where I solve for k, because I know it's a tricky one. So there you go. We can also look at a mass moving in a circle as a simple harmonic oscillator, because really, if you think about it, okay, it's difficult to describe this. So if you really want to visualize this, you need to go to Crash Course and look at their video on simple harmonic motion. And it has just like the most beautiful animation of this happening. But anyways, think of a thing moving in a circle, okay? So here I got it like a mass here, and it's moving around in this circle, okay? So it's going around and around and around and around, okay? If you were to look at this circle, but from the front, Okay, so right now we're looking at the aerial view of it going around and around like from above. What if I were to look at it from the front? Would it look like it's going in a circle like that? No, it might just look like it's going back and forth. So when it's at this position, it might look like it's right here. And when it's at this position, it might look like it's right here. And when it's here, it looks like it's at equilibrium. And when it's here, it looks like it's squished. And when it's here, it looks like it's squished even more. Oh my goodness. So really, if you take something that's going in a circle, but you look at it from the side, it just looks like a mass on a spring. So these two things are so closely related, which is really cool. So actually, we've already gone over simple harmonic motion when we're going over circular motion. So you guys already know a bunch of stuff about it, which I think is pretty cool. And I just think it's really cool that a mass going in a circle, when you look at it from the side, looks exactly the same as a mass on a spring. I don't know. I guess I'm amused by it, like simple things. But, you know, it's what a physics teacher does, is they just like take a tiny little thing and then like find out an insane amount of things about it. So that's just kind of what it's all about. Right? Right. Okay, let's go on to talking about forces and energies. With simple harmonic motion, and specifically we are going to kind of really focus in on springs here. Okay, so remember, simple harmonic oscillator, we call it an SHO, or SHM is simple harmonic motion, just because I don't want to write all those words all the time. Oh my goodness. But as we know, restoring force directly proportional to displacement, but force is also equal to mass times acceleration. So we know acceleration is directly proportional to restoring force. Okay? And that's because, again, we know force is equal to mass times acceleration, especially net force. And if the restoring force is the only force at work, then basically our restoring force is mass times acceleration. But the force isn't constant, it's varying with the displacement, right? So the more displacement there is, then the more force there is, at least at the beginning. And of course, there's lots of acceleration when there's lots of force, but when there's no restoring force, there's no acceleration. So here it is. We finally reached it. Acceleration is not constant. Acceleration is changing. So we are actually going to go over some situations where acceleration is not constant. I said we aren't, and I'm more talking about when things are moving in a straight line, okay? And it's not like we're going to try and find acceleration like at every point or anything like that, or average acceleration. So really, we just want to know acceleration at certain points in the motion, and when is it maximum and minimum and stuff like that, okay? So if we want to know that, we need to know about the energy of a simple harmonic oscillator as well. And again, this is specifically talking about a mass spring system. We already talked about energies of the pendulum and when it's at maximum potential and maximum kinetic. So again, this is, of course, when we're talking about a simple harmonic oscillator that has no friction, then it's just the sum of kinetic and potential energies, okay? But in this case, if we're looking at, say, for example, if we're looking at a horizontal spring, then we really only have kinetic and spring potential, okay? And so that's what's really nice about this. So energy, mechanical energy at any point in a spring's oscillation should be the sum of kinetic energy and its spring potential energy, okay? And of course, that always, the spring potential energy depends on how far it is from equilibrium. Kinetic energy depends on how fast it's going, okay? And then we use a special thing for when it's at its maximum displacement. Instead of using X, we use A, because A is amplitude. Remember, that's one of the definitions that gave you under simple harmonic oscillators. And that's one that's really, really, really important to note, okay? So what are we going to do? We're going to look at our energy and our forces at kind of the two maximums here. So full compression and extension, and when it's at equilibrium, because I really want to look at what's going on here. Okay? So let's start with full extension, which this is the same as at full compression. Okay? So full extension / compression. And that should be the same thing happening. Okay, except for one's compressed, right? And one's extended. So this is extension in the picture, but compressed would be when it's really, really close together. Okay, but it will have the same displacement in simple harmonic oscillators. Okay, so what's happening at this point? Well, at this point, when it's at its full extension, it's gone as far away from its equilibrium it's going to, and it's going to turn back the other way. So what do I know about something when it's going from one direction to the other? It needs to stop for a split second in the middle. So the first thing we know about at this point is that the velocity is 0. Okay? Because again, for something to change directions, its velocity has to go to 0 for a split second. If the velocity is 0, what's the kinetic energy? It's of course 0. And then potential energy is at its maximum, which makes total sense, because what's spring potential energy again? Spring potential energy is 1/2 kx squared. X is at its maximum here. It's farthest away from its equilibrium point than it's ever going to be. Okay, so of course we have our maximum spring potential. And again, this is the same as if it were at its full compression as well, right? Because we're assuming that the compression is the same distance away from the full extension. Okay, so it's really, really important to note they're the same for full compression and full extension. Okay, so those are a few really important things. Okay, so here's where we have 0 kinetic energy and maximum spring potential. And then of course at equilibrium, guess what your spring potential is? If spring potential is equal to 1/2 kx squared, guess what x is if it's at equilibrium? X is at 0. So our spring potential energy is of course 0. So isn't that nice? So if my spring potential energy is 0, what has all my energy converted to? Must have converted to kinetic energy, okay? So I know here, potential energy 0, kinetic energy is at its maximum, which means our velocity is at its maximum at the equilibrium. Okay, so of course, where the previous position was full extension or compression, this is where it's at equilibrium. Okay, so again, I just have a bunch of notes here, basically saying what I just said, but I'm going to go over them again. So of course, at our extremes, that's full compression or full extension. Okay, that's what that means. Full compression or extension. Then the mass has to stop to change direction. So of course our velocity is 0. So our x is a amplitude, right? Because amplitude is our maximum extension or maximum compression, which should be the same value. So of course our potential energy is at a maximum. So then I want to say, what does that mean for force? So again, we want to look at restoring force. What does the force want to do? It always wants to put it back at equilibrium. Okay, so think about that also. So if this is as far away from its equilibrium as it's going to get, guess what? The force here is probably at its maximum, isn't it? Right? Because it wants to get it back over there. It always wants to get it back to equilibrium. So whether it's here at full extension or if it's here at full compression, guess what? Your force is wanting to get it back to equilibrium, always. But when it's at equilibrium, what do you think my force is here? Remember, force always wants to get it to equilibrium, and it's at equilibrium. So the force is like, yay, I'm good, I'm done. Okay, so that's what's happening. So the force is maximum here, and then of course it's just getting smaller and smaller and smaller as it moves towards equilibrium. Okay, and so if that's happening to my force, if my force is at its maximum when it's at full compression or extension, acceleration, what's that going to be? Well, we know they are directly proportional, right? Force is equal to mass times acceleration. So whatever happens to the force, the same thing happens to acceleration. Okay, so if force is at its maximum, then acceleration is at its maximum. If force halves, acceleration is half, right? That's how force and acceleration relate to each other. So if I'm looking for mechanical energy, at this point, I know I have no kinetic energy because my velocity is 0. So my full mechanical energy at this point will just be equal to the maximum spring potential energy. And so at that point, instead of putting X in, I put in this A for amplitude. Say this is at its full compression, full extension, okay? This is as far as it's going to stretch away from its equilibrium, okay? And then, of course, at equilibrium, I, again, already pretty much talked about this. So our velocity is at its maximum, okay, at equilibrium, because again, acceleration has had this whole thing to time to work on it. So of course, acceleration is because it's accelerating towards its what am I trying to say? Oh my goodness. Equilibrium, then it's going fastest at the equilibrium, okay? And this is the point at which displacement is 0, so we have maximum kinetic energy and no potential energy here, okay? Because all the potential energy due to a spring force and due to spring potential energy, you know, they're done. They're like, oh, we're back at equilibrium. So here's the weird thing that, again, the force done by the spring is always trying to get back to equilibrium. So basically, at that point, my force is 0 because it's saying, yay, I'm at equilibrium. Now, here's the weird thing, is that at that moment, my acceleration is also 0. Why? Because force is equal to mass times acceleration. We know the mass ain't changing, so if force is 0, guess what? Acceleration has to be 0, okay? And people have a hard time with that because they're like, but it's maximum velocity. Why isn't it accelerating? Well, it accelerates until it gets to equilibrium. Then for a split second, it's going at a nice constant velocity because it's like, oh, I'm good here. I like it here. But then, of course, because of inertia, it keeps going the other way. But then the spring starts working again and then puts a force on it. And then, of course, it slows down, which is also a form of acceleration. Okay, so remember, there's only acceleration when there's an unbalanced force. At equilibrium, the force is balanced. We've brought balance to the force, okay? It's pretty fantastic. Okay, so energy at this point at the equilibrium. So remember, this is when spring potential energy is 0 because your displacement from your equilibrium is 0, and so all your energy is just kinetic energy, okay? It is so important that you understand these two things, okay? What's happening at your extremes and what's happening at equilibrium. It's really important that you understand this, okay? Because again, you're going to be asked questions on this that just assume you already know all this, okay? And just a really quick thing, just so you know what the acceleration looks like when it's changing, okay? And again, this is just another way to show you how acceleration does reach 0. Okay, so at this point, when it's fully compressed, my acceleration is to the right because it's, of course, we know the force is to the right because it's trying to get it back there. So my acceleration starts positive, okay, but my displacement is negative. And then what's happening to the acceleration? So it's going down, down, down until it reaches equilibrium, at which point the acceleration does go to 0 for a split second. But then, of course, as soon as it goes past equilibrium, my displacement's now positive because it's to the right of the equilibrium, but now my acceleration's negative because guess what, over here, it wants to push it back that way, okay? So that's why my acceleration is at 0 just for a moment there, and that's when it's at equilibrium, okay? So it's kind of the same idea that if something's changing directions, the velocity's got to go to 0 at some point. This one, it's not the velocity that's changing direction, it's the forces that are changing direction at equilibrium, right? At equilibrium, force is 0 for a quick moment, but just to the left of equilibrium, the force is going to the right, and just to the right of equilibrium, the force is going to the left, okay? And so then the same thing's happening to your acceleration. And then your velocity. So this is the only time we've really seen slanted line on an acceleration time graph, or actually this isn't even acceleration time, this is acceleration displacement, but that doesn't mean that we need a curved velocity. So my velocity is definitely not consistent. It's changing. It's always changing, okay? And it's not even changing at a constant rate because, of course, the acceleration is not constant. So we see a curved line on that velocity displacement graph, okay? So that's what's happening with your acceleration. Just another way to explain that. Okay, let's just talk about intermediate points really quickly. Of course, at intermediate points, then it's not a maximum. So it's going to be part kinetic, part potential. Okay, so if you ever had to find something at an intermediate point, again, that's not quite at full extension or compression, and it's not at equilibrium, it's in between those two, then you have a bit of both, okay? So of course, if you need to solve for any variable, you probably either want one of your maximums or equilibrium to have, so you can figure out your total mechanical energy. And then of course, you're gonna make any two of these kind of parts of the equation work, okay? So of course, this is an intermediate part. So the sum of kinetic and potential at any point is equal to the kinetic energy, the maximum kinetic energy, and of course we know that's at equilibrium, okay? And we know that's equal to the maximum spring potential energy, and that is at your maximum compression or extension, which is really your maximum displacement, which is of course your amplitude. And then this is another intermediate point. Of course, when you actually have both of them, that's going to be any of your intermediate points. So usually if you want, what's the velocity when it's this far away from displacement or away from its equilibrium, then you either need your maximum kinetic energy when it's at equilibrium or your maximum displacement, your maximum spring potential energy, okay, when kinetic energy is 0, because then it's easier to make, one of the intermediate points equal to one of the absolutes, okay? So that's how we're going to do that. So we're going to do a few examples here. There's definitely a few here, so I know this is a long video. So if you need to take a break just to give your brain a little break, then this would probably be the time, okay? All right, welcome back. I mean, if you gave your brain a break, but maybe you're just like, nope, soldier on through. So first, I'm just going to go over and make sure that we understand proportionalities before we actually do anything with calculations. Okay, so I want to know if the amplitude of a simple harmonic oscillator is doubled, what happens to the energy of the system? Okay, so amplitude, what does amplitude mean? That's maximum displacement. Okay, that's what the amplitude is. So, energy of the system. How is energy related to amplitude? Well, of course, we know energy is 1/2 kx squared, but then when x is at its maximum displacement, that's a. So it's equal to 1/2 ka squared. So here we see that energy is proportional to the amplitude squared. So what happens? If I double the energy, double the amplitude, then I need to square that, and the energy is 2 squared, 4 times as much. Okay, so that's what we know happens to energy when we double the amplitude. Let's talk about the velocity. This one's a little bit more difficult, okay? So I want to know what happens to the velocity. Well, we know the maximum velocity, so mv squared maximum. This should numerically equal to the maximum spring potential, right? So what do we see here? We see velocity squared is proportional to the amplitude squared. So that's just a fancy way of saying they're directly proportional. Okay, so they're both being squared. So really, velocity is directly proportional to amplitude. So if I double the amplitude, I double the maximum velocity. Okay. The maximum force. So again, if I double the amplitude, what happens to the force? Okay, I need to look at a different equation. So remember, how is force related to springs? Oh, we have an equation for that. Force is equal to kx, right? Negative kx, but here I just care about what happens. I don't care about, like, I just want the magnitude, not anything else. And then again, when x is at its absolute, or it's at its maximum, that we call that amplitude, A. So force here we see is directly proportional to A because nothing's happening to the force or the amplitude, so they are just directly proportional. So whatever happens to the amplitude happens to the force, so this means we'd also be doubling the force. Okay, and what happens in the maximum acceleration? Well, this is a time where I'm actually not going to use the amplitude to figure out acceleration. I'm just going to look at the part before it, because again, I know force is directly proportional to acceleration because force is equal to mass times acceleration. So if I double the force, then I must be doubling the maximum acceleration. And how do I know it's doubling of the force? Because I double the amplitude. So doubling the amplitude doubles the force, which doubles the acceleration. Okay, so that is how proportionality works, and it is always important to know that kind of stuff. So you know that if I double the amplitude, i.e. instead of stretching a spring, I don't know, 5 centimeters, I stretch it 10 centimeters. What's going to happen to everything? Okay, and that's what I need you to know. Let's do another example, but now with some actual calculations. Okay, this one's going to be a lot. So let's really think through it step by step by step. Okay, so spring stretches 0.15 meters when a 0.3 kilogram mass is hung from it. So this is going to be a vertical spring because we have the language of hanging. That means something is vertical, right? So we don't have a horizontal spring here. The spring is then stretched an additional 0.1 meters from this equilibrium point and released. Okay, so again, the spring stretches when it's hung from it, so we're guessing that's its new equilibrium, and now it's being stretched an additional 0.1 meters, and then it's released. So then, of course, we know it's going to do what? It's going to oscillate. It's going to be simple harmonic oscillator. It's going to go back and forth, back and forth, back and forth. Okay, so I need to find out a few things, but the first thing I'm going to figure out is the spring constant. Okay, I'm just going to completely start this on another page. So what do I want to do when I'm having a bit of a hard time visualizing everything and figuring out what's going on? Well, I am going to draw a diagram. Of course, right? So my spring starts out like this. It's just a happy little spring that's, you know, just hanging there. And then what happens? Somebody comes along and hangs a mass on it. So what does that do? It stretches it out a little bit. Okay? So there we go. It has a mass on it. So the distance from here to here is what? This is 150 meters. But this is really its new equilibrium once the mass is hanging on it. So I'm going to say that's when x is equal to 0. That's the new equilibrium. Okay, and then of course it's stretched an additional 0.1 meters. So now I'm exaggerating a little bit just to make it easier to draw. Okay, and then of course its amplitude is 0.1 because that's how much it's being stretched. So that's that distance now. Okay, so that's what's happening. So first thing it asked me for was its spring constant. What the heck is that? Okay, well, I'm going to use this one in the middle here to help me figure out the spring constant, because at this point I know spring force is upwards, and guess what's downwards? Gravitational force. And so at this point, I know they are equal and opposite. How do I know that? Because I know the sum of the forces is equal to mass times acceleration. And this is exactly why I chose this one, because I know there's no additional force and it's staying still, so I know acceleration 0. Okay, so that means I'm going to go ahead and make downwards positive. Why? Because remember when we had the force of the spring is equal to kx, but it's actually equal to negative kx. Well, then this way I can say Fg is positive minus force of the spring is equal to 0. And then it's taking care of that negative kx there for me, which is really, really nice. And so then I don't have to worry about it afterwards. So it's kind of the same when, you know, we make upwards positive, but we subtract FG, and then you want to like make 9.81 negative, but we already counted for that. So it's kind of the same thing. Okay. So what does that mean? It means that mg is equal to positive kx, because we already have the negative kx there. It's already been accounted for, and so there we go. Okay, so what happens here? Well, we need to find the spring constant, so I'm going to divide both sides by x. So I get mg divided by x. Okay, and then what I'm going to do, I'm going to plug in my numbers. My mass, what was that again? It was 0.3. G, that's pretty obvious. We know what that is. And x, what's x in this situation? So this is how much it was stretched from its original point, okay? And that is 0.150 meters. So that's why I still want that value, right? But once it's oscillating, I'm completely ignoring this stuff, right? I'm completely ignoring that 0.15, because once it's oscillating, it's the 0.1 we care about. Okay, but we're not talking about it oscillating yet, so that's why I want to talk about that 0.15. So what do we get? We get a spring constant K of 19.6 newtons per meter. Okay, there we go. We got it. We figured it out. So that's actually really using some stuff from last unit. So that's something you could have already figured out without all the additional information. Part B, what's the amplitude of oscillation? A. So again, we know how much it was stretched beyond its equilibrium. And so in a simple harmonic oscillator, we're going to assume that it stretches down that far, so goes back up that far, stretches down that far, goes back up that far, and just keeps doing that. So since the spring was stretched 0.1 meters, .10 meters from equilibrium. I'm just using equal because I don't want to write it all out. And it was given no initial speed, like not given an extra push, and given no extra push, right? Then we know that our amplitude, which is our maximum displacement, is the same. That's basically what it's saying. Okay, so that's what I know my amplitude to be, which is, of course, my maximum displacement. So we're talking about once it's oscillating. Okay, so the first step is really just to show us how far it went when the mass hung on it. And now this is my new equilibrium. So from after point B, we're talking about oscillating. I'm just going to completely ignore that first step. Okay, because I just don't care about it anymore. Now I really only care about what's happening once it's oscillating. So here, this little step 2 here, that's equilibrium. Step 3 is full extension. And then, of course, I won't draw step 4, but step 4 would be like when it goes back to full, or when it goes up to full compression. Okay, so let's keep going. Part C, what did it say? It says, what's the maximum velocity? So again, we know when is the maximum velocity again? It's when it's at equilibrium. Okay, so this is maximum velocity right here. Okay. And so we know that's because it has the maximum kinetic energy there. We also know another place where it has a maximum energy. But basically, anytime you have velocity, we're probably going to be dealing with energy and kinetic energy. So we know the sum of energies at any one point is equal to the sum of energies at any other point. But of course, I'm going to choose those 2 points very, very specially. And of course, I'm going to talk about the point at which I have maximum velocity because, well, that's what I'm looking for, right? And I know that's equal to the maximum spring potential energy, which is when our x is at its amplitude, which, fancy that, I figured that out, or we know that it was given to us. I didn't even have to figure it out, it was given to us. Okay, so what's going to happen here? We've got to solve for velocity. So by the way, when you multiply both sides by 2, inevitably, to get rid of this 1/2, what happens? 1/2 times 2 is just 1, so they technically kind of cancel out. Okay, so we get a velocity, a maximum velocity. Actually, instead of calling it Vmax, I'm going to call it V naught, okay, of, just because it's shorter, our equation would be K squared divided by M, all square rooted. Okay, so I'm going to plug in those numbers. And I get a maximum velocity of 0.809 meters per second. So no, it's not going that fast, but really you didn't really stretch it that far. Like, you know, so it's 10 centimeters. I mean, it's not bad, but not that far. Alrighty, so there we go. We have our maximum speed. Oh my goodness, we still have so much left. What else we got? The magnitude of the velocity when the mass is 0.05 meters from equilibrium. Okay, so is that its amplitude? No, this is somewhere in the middle, isn't it? Okay, so when I'm looking at point D, if we know that its equilibrium is there, and if we know full expression or compression or extension, well, this would be extension is right there, that's at 0.1 meters. It's asking for what's the velocity when the mass is 0.05 meters. So it's actually asking for the velocity that's like halfway in between these two. So at this point, what's the velocity? Okay, so what's really important about visualizing that is it's just helpful to know that, oh, we're not at an extreme anymore. We're not at an equilibrium or at an extreme. So this is going to be one of the situations where I have to use a mixture of potential and kinetic. Once it's at half, so this is half of the distance, right, which is 0.050 meters. Why is the velocity not just half? Is the acceleration constant? No, it certainly is not. Even if the acceleration was constant, the velocity wouldn't be at half. So, yeah, never assume that. So in this case, we're still going to use the fact that all the initial energies added up should equal to the final energies added up. But in this case, one of my initial will have to be, or final, they'll have to be kind of the in-between, okay? So again, it does not matter which one you choose because we know both maximums at this point. We know the maximum kinetic and we know the maximum spring potential. I'm just erring on the side of using the maximum spring potential because that value was given to us in the question and the velocity was not. So just in case I did something wrong there, I'm going to go ahead and use maximum spring potential, okay? So I'm going to call this my initial position and this is my final one, okay? But again, doesn't matter. So my initial is the maximum spring potential, so I know there's no kinetic energy there, but of course I want something that's a little bit in between, so of course my whole energy there is a mixture of kinetic and spring potential. Okay, and in here I can't call displacement A because that's only when it's the amplitude, when it's at the maximum, so it's back to being X. But the X is 0.05 in this situation, okay? So what are we trying to find? We're trying to find V here, okay? So we're gonna rearrange for that because we have everything else. We have K, we have the amplitude, which is the full amount that it was stretched. We have the mass, we have the displacement that it's at right now, so we got everything. So again, if I go ahead and multiply both sides by 2 to like get rid of this, well, guess what? All the 1/2s go. So I'm just going to do that right now just to make it be a bit easier. And then what do we get for our velocity? Well, what we end up getting is we have to take the maximum spring potential and subtract from it the spring potential of the kind of intermediate step, okay? And then I'm going to divide that by the mass and square root it. And that's how I'm going to get my velocity. And I'm definitely running out of room here, so I'm going to go over here. Okay, so again, this is what we had. And I'm going to go ahead and plug in those numbers. And when I do that, I get a velocity of 0.700 meters per second. I do need 3 significant digits throughout this whole thing, so I'm always using 3 significant digits. Okay, so notice that is less than the maximum velocity, but it's definitely not half, right? Because that velocity, it's just not changing at the same rate that the displacement is. Oh, yes, we have one more point here. Ugh. What is the magnitude of the maximum acceleration? Okay, well, here we know acceleration will be related to force, okay? When do we have the greatest force? That's what we need to ask ourselves. Do you remember? We have the greatest force when it's furthest away from equilibrium, because that's what the force does. It wants to take it back to equilibrium, okay? So when we're doing part, oh goodness, what even part is this? Part E now. That's what we're doing. Oopsie. We know that we have maximum force. So maximum acceleration occurs when we have maximum force, which is also when we have maximum displacement. Okay? Because, of course, that's when the force really wants to get it back. That's when it most wants to get it back to equilibrium, is when it's furthest away from it. So in this case, our x displacement is our amplitude A, which is 0.0100 meters. Okay, so when I look at force is equal to mass times acceleration, here my net force is my spring force, okay? At this point, we don't care about gravity because we already took care of that as part of the acceleration, okay? So again, what's my spring force here? This is where we do have to keep negative k times x, which again, x here is A. That's equal to mass times acceleration, okay? And I'm going to go ahead and say that upwards is positive, okay? And you'll see why. So my acceleration at this point should equal to negative k A divided by mass, okay? But what direction is my displacement at this point? It's below equilibrium, so therefore it is negative, okay? So I have negative 19.6 newtons per meter, but my amplitude here is also negative because it's below equilibrium. Okay, so that's going to make my acceleration give it the correct direction there. So that's 0.300 kilograms. Dividing that by, and then I get an acceleration of 6.54 meters per second squared. So it's accelerating, it's changing its speed real fast. I do have one more example. I know you're going, oh my goodness, how long is this going to go on for? But I promise this is a much shorter example with much less talking. So we have a mass sitting on a horizontal frictionless surface. So it's so much nicer when it's horizontal, because then we don't have to think about gravity and how that's counteracting spring force and all that fun stuff. Okay, so frictionless surface. So yay, that's also good, because then we know it's a simple harmonic oscillator. It's attached to one end of a spring. The other end is fixed to a wall. Okay, so we have 3.0 joules of work. Oh, that's nice. Kind of seems like it's giving us some energy there. So 3.0 joules of work is required to compress a spring by 0.12 meters. Also seems like it's giving us our maximum displacement, which is really nice. So already I can see like, oh, 3 joules of work is equal to change in energy. So you just gave me a kind of energy there. You also gave me the amplitude. So that's nice. If the mass is released from rest, oh, also nice. With the spring compressed, it experiences a maximum acceleration of 15 meters per second squared. We know when the maximum acceleration is, so this is actually giving us a ton. Oh, nice. Okay, A, we're going to find the spring constant. So how are we going to do that? Oh, well, actually, really, when you think of it, it's kind of easy, because it gave us how much work we had to do to compress it, and it gave us its maximum compression. So really, we know that work is equal to change in energy. What did it just change? What energy did it change? It changed the spring potential energy. Before it had no kinetic and no nothing. And after it pressed it, well, still no kinetic, but guess what? We have spring potential energy. Okay? So my whole change in energy was really just changing the spring potential energy. Oh my goodness, what's spring potential energy equal to? 1/2 kx squared, but here my x is the amplitude. Oh my goodness, so how the heck am I going to find k? Well, it looks like I have everything but k in this equation, so, I mean, how could you not at this point, right? So nice and easy. So that's how I'm going to find it. Let's plug in those numbers. And we get a spring constant. I only want 2 significant digits in this one, so I need to use scientific notation. I get 4.2 times 10 to the 2 newtons per meter. Oh my goodness, we're already half done. See, I told you this one would be better. I told you, I promised. Now I want the mass. We were given the maximum acceleration. What's special about the maximum acceleration? When does that happen? That happens when you have maximum force and we have maximum acceleration. Do we have force? No. Can we find force? What's the force due to? Spring. Oh, what's spring force equal to? Kx. Do I have K? Yes. Do I have X? Yes. Oh my goodness, I have the spring force. Okay, so again, I told you this one would be so much nicer because really we know max force is when we have maximum acceleration, and of course we know force is equal to mass times acceleration. So there you go. Okay, so if I'm looking at spring force, is my total net force equal to mass times acceleration, and of course spring force is negative kx. That's equal to mass times acceleration. Here I don't really know which way. I guess like if we're gonna, let's go ahead and say like it was compressed to the left. So my displacement is negative, and then I'll say right is positive, so my acceleration is positive. But here you might get a negative acceleration, and that's okay. It's just saying that acceleration is going the opposite direction of displacement, which it is. Okay, that's all it's saying. Okay, so if I'm looking for mass here, then really that's just going to be negative kx divided by acceleration, or this is when, of course, we have a amplitude for x, so you can use x, you can use a, they're the same thing here. Okay, so again we found that k, which was 4.2 times 10 to the 2 newtons per meter, times my amplitude. Here again I made my to the right positive, and I'm assuming that it's like a spring that was like, this is its equilibrium, but it's like pushed, so it's like actually right here right now. Okay, so the displacement's to the left, so the acceleration will be to the right. And then divide that by the maximum acceleration, which was just given to you. This is a nice one, stuff's just given to you. Okay, so we get a mass of 3.3 kilograms. I promised that one would be shorter, see? So whenever you see a horizontal frictionless surface spring, rejoice, because life is just going to be so much easier. Okay, I know, long one today, you guys, so I'm just going to stop talking.